In this video, we'll be discussing section 13.6. This is directional derivatives. We mentioned in the partial derivatives section, I talked about that we would eventually get to fully directional derivatives. Here it is. So this will allow us to get a derivative in any direction that we want. The only ones that we have focused on so far is in the x direction and in the y direction, but not in any direction we want. Okay, with the theory of this, usually I'm happy to go through the context of everything, work through the problem, and try to show you where it comes from. The problem is with this method and the way this book does it, there is a jump in here that I don't really care for, and what I'm going to do for this, instead of using video time for this, I am going to do something I usually don't. We are going to use the formula, and I'm going to leave this. I posted everything from the book in your notes, so you'd have it. I also would recommend checking out some other videos if you care about where this comes from. So again, what we're doing, let's grasp this. What we're going to eventually do is we're going to have a point on our curve. So like here, they picked a point right here, and they said, hey, we want the derivative, but we want it in the direction of this vector above here, right? We want it in that direction. So what they're trying to do is they are finding a tangent line in the direction of u off of that curve. They use the distance formula, and then they use the difference quotient to finally get to this definition, right? So this is the actual formal definition. We aren't going to do anything with that, but look at it. That's what, if we would have taken the time to run through this, the theory of how they get to that. And then they're like, okay, that's the definition. This is where it comes from, right? But we're going to use this derivative, this definition of the directional derivative. So as you can tell, if you look here, the directional derivative in the direction of u, okay, I do want to highlight this because this is a big thing. This is where students mess up. The direction giving us the direction that they want the derivative in must be a unit vector. If they give me a theta, I can find the unit vector like that, cosine, right? That makes sense. That's the x coordinate. Sine is our y coordinate, so it makes sense that our unit vector would be made out of those two. Now, let's take a look at our formula. We have the x coordinate with cosine, with our partial with x. There's no I or j. Remember, a derivative is a number, right? We just have to know what direction it's in. And then we add it to the y component sine of our unit vector times our partial with respect to y here. Okay, so I am going to talk about this directional derivative within an example. So let's get at it. Okay, so here's this example. Find the derivative of this function at this point, right, in the direction of the vector that makes an angle of pi over 6 with the x-axis. Okay, so this is where we are creating our unit, and the unit vector is going to be in 2D, telling us where to go. If I have some angle of pi over 6, I can use trig to come up with my x and y components. So this unit vector is just cosine of that angle, pi over 6. That would give me this, right? That's I. It is a vector. Plus sine of pi over 6. That is my y value. All right, so let's get our u here. Our u then is the vector. Okay, we get radical 3 over 2 for cosine of pi over 6, comma, and then sine of pi over 6 is 1/2. So there's my unit vector. So I have some type of function. This is my x and my y axis here that's flat, right? And we're graphing a surface on top of that, the z's coming out at us. We want to know at this point 1, 2, right? We want to know which way is the graph pointing, right? Or what's the tangent, sorry, the tangent line, the slope of the tangent line. Sorry, my brain, I let it get too far ahead. All right, we need that derivative. So the directional derivative of some function, let's write down this formula real quick. I recommend when you're doing homework to write down formulas as you're doing every single problem. So this is cosine theta, and then the y partial was sine theta. All right, we already have cosine and sine theta. We already figured those out. So all we have to do now is we need the partial with respect to x of this function. So we get 3x squared minus 4x. We also want the partial with respect to y, right? This goes to 0, that goes to 0, which leaves us with 3y squared. All right, so how we compute our directional derivative is we say the directional derivative in the direction of u of f x, y is equal to, okay, I got 3x squared minus 4x times radical 3 over 2. That's the cosine. Plus, it's not a vector, it's a derivative. So we have a number, 3y squared times 1/2. Right? They wanted us to find it at a certain point here. The point being 1, 2. So all I got to do is plug in 1, 2. So we get 3 minus 4 square root of 3 over 2 plus, and then just the y there, 2 squared is 4 times 3 is 12 divided by 2 is 6. So this ends up being 6 minus radical 3 over 2. All right, that is the derivative, the directional derivative at 1, 2 of this function. What this tells me is this is the slope of the tangent line. Let's write this. Slope of tangent line to f of x, the surface, at the point 1, 2, in the direction of u. So very important that you say the u part, because if I say it has a slope of 6 minus radical 3 over 2, at the point 1, 2, you would say, well, in which direction, right? In the x direction, y direction, do I have a vector that I have to follow? Anything like that goes along that vector. So we need to know the direction. So in 2 dimensions, we didn't really need to know it because we only had the y and the x. But now that we have that 3-dimensional surface, we can actually turn that tangent line in any direction that we want, giving us infinite tangent lines. So this is why we need this directional derivative to help us with all the other directions that are not x and y. Okay, I have a small discussion here, just working our way into this new idea. Okay, I have the directional derivative is equal to this. Okay, the only thing I'm changing here is I'm going to call these those are u1 and u2. Okay, u1 and u2 will be the vector, the unit vector, just a short name for it. Right? Notice here that we have a dot product happening. We have fx, the partial with respect to x, partial with respect to y, that vector dotted with u1, comma u2. Take a moment, remind yourself of the dot product formula. We multiply our coordinates and add them together. Okay, this thing right here is noted. We write this a special way. This is called the gradient, and we do this like upside down delta f. And then this is my unit vector. So this thing right here is called the gradient. This is super important, super useful. I've seen this used in real life. I'll give you, once we get there, I'll start talking about where I see it. Del F is how we say it, or you can say gradient of F. Those are the two ways you would say that. I'm going to write out what that is down here. All right, so del F is Fxi plus Fyj. Super important. Okay, a couple things I want you to know. du, the directional derivative, right, of f is a slope. I'm making this point because we're going to make a differentiation here. Is a slope, a scalar, not a vector, right? That's the directional derivative, not del f, not the gradient, not a vector. We're writing this to compare with del f, though. Del f is a vector. What am I writing? Vector is a vector. I'm going to write down the definition of du, the directional derivative here, just to make sure you understand that u1, that u1 and u2 are just cosine and sine, if you wanted to think about it that way as well. Du, the directional derivative, is a slope, but it comes out as a number. Notice no i's or j's or k's. Del f is a vector. What this does is this relates to the grade. And what I mean by grade is the climb, right, the steepness of the surface We'll leave it there. Relates to the grade or climb of the surface. That means like how steep is it? How far does it go? Stuff like that. It has a really cool property. All right, so the properties of this, let's go ahead and talk about it, is that if del F is 0, then the directional derivative is also 0 for any u, in any direction. This will make sense in a minute why. Remember, this is our directional derivative. It actually has its maximum value of this, and this happens when u is a constant multiple of f. What this means is that it runs in the direction of del f. Del f is a vector. So what does that mean? Well, that means that del f actually is a maximum, right? Del f is it's a vector. It can't be a maximum, but if I take the magnitude of it, that is a maximum value for slope at that point. That will give us, what does that mean? Let's say that again, just to make sure you're grasping it. If I want a maximum slope, I'm at this point. Sitting at a point, and I'm looking 360 degrees around me, and I'm on this surface, and I'm trying to decide the steepest way. I'm going to go up the fastest, right? The biggest slope from that point. That biggest slope is the magnitude of del F. Del's going to turn into something else more too later, so don't just call it del. Del F, the gradient. What that means is the gradient is the steepest path. Remember, the gradient is a vector from a point. It is the steepest path on that surface. It's the quickest way of increase. Why this is important, let's prove it first, and then I'll talk about some of the applications that I've seen in my actual life. So let's start with this directional derivative. We're going to do somewhat of a proof here. We're just going to talk about why this is true. Why is it the maximum? Okay, so I know that I can find the directional derivative by taking del F and dotting it with my unit vector. Now, hopefully you remember this definition, maybe not, from chapter 11. I can actually do this, the dot product of del F and u, by finding the magnitude of F, the magnitude of u, times the cosine of theta. Okay, this means that the directional derivative is equal to, all right, I'm going to keep my del F, but the magnitude of a unit vector, well, if it's a unit vector, the magnitude is 1, leaving me with this. All right, this is a constant. That is the gradient of f in that direction, right? That is the slope of that vector from that point, right? Or not the slope, but the length, rather. It's the magnitude. The length of that vector, not the slope. The length of that vector. If I take the length of that vector and multiply by cosine, I get a derivative. Okay, here's the deal, though, with that cosine. Remember that cosine is stuck between -1 and 1. So what that means is that this derivative, because this part isn't going to change. That's just a constant, right? That's the magnitude. That's going to get its biggest value when cosine is 1. It's going to get its smallest value when cosine is -1. So we're going to write a statement for that. Max value of cosine theta equals 1. So we get a max value of cosine equals 1 when theta equals 0. That's when that happens, is 0. So the angle between del F and u is 0. Thus, I guess I'll put that 0 over here. 0. Thus, the derivative here would be parallel, or those two would be parallel. Del F, would be parallel with the unit vector. What that means is that since that cosine would be a 1, it would give me all of this magnitude, right? The magnitude here, this is what I'm talking about. It would give me all of that if cosine is 1. If it's less than 1, it's going to just give me, because if I multiply by something like 0.25, that gives me 25% of what I'm talking about, right? 0.25 gives me a fractional part. So if I multiply something less than 1, it just gives me a fractional part of del f, which means of the magnitude of del f, which becomes less steep. Okay, so huge point. Del f gives the vector for the steepest grade of the surface at a point. That is the steepest path from the point you are standing or the particle standing. The del f, the gradient, will show me how to increase the fastest. With that, though, and this makes sense, if this is the fastest, well, if I let cosine equal -1, that spits out a negative magnitude. Well, that magnitude is the biggest one, so if it's a negative, it's going to be the smallest one. So while the positive magnitude of del f is the biggest slope that we could have from that point, negative del f is the smallest slope that we could have. This makes sense because if there was something smaller than negative magnitude of delta f, right, gradient f, then that wasn't its maximum. I hope that makes sense to you. All right, we are going to jump to some examples now. Using these definitions, all right? So I'm going to I write del f every time I start, just to help me memorize. Del f is equal to fxi plus fyj. So I need each part of that. So I need fx, right? So that is the partial derivative of 1 over x squared. I'm going to think about x squared plus y squared to the -1. That's how I'm going to think about it. And you can put a 1 out here if you want to do that. -1 comes down, x squared plus y squared. That goes down to a -2, and then times the partial of the inside is with respect to x is 2x. So we get -2x over x squared plus y squared squared. Now the partial of y, same idea. If you notice, like nothing on that formula looks different. We call this symmetric. And what this means is I'm just going to get that same thing, but a y on top. If you don't believe me, go ahead and work it out. All right, and then they just want the gradient at that point. So del f at 1, 2 is equal to, hold on, we should probably write just del f. Let's write that first. That's going to be -2x over x squared plus y squared squared I plus -2y over the same thing. I'm going to be lazy there for a minute, over j. All right, so we have that, and now I'm just plugging in those values. I plug in 1. Let's do 1 and 2 on the bottom and go ahead and get that. We got 1 squared plus 2 squared is 5. 5 squared is 25. So I got a 25 on the bottom, but a 1 up top makes a -2i minus, okay, I plug in y there. Okay, I know the bottom is still 25 because it's the same thing, but I plug in 2 there and I get a 4. This is j. That's all they're wanting. So this vector, and let's make a point, this is not slope. Del f is not slope. Del f is the steepest path. Now, if I'm standing at 1, 2, and I go up the vector -2 over 25 in the x direction and -4 over 25 in the y direction, I will be going up the steepest hill I can climb on this surface from that point, the most direct route up. All right, let's get a few more. Right, del f, I write down the definition again. This helps me memorize it. All right, so I need each part. I need fx. Oh, and then notice, maybe this is a bit different, x, y, and z. How we actually change this, you'll like it. It's not a big add here. One sec, my screen's loading all weird. I just take it with respect to z, and then throw a k component. All right, so I got fx partial. That is a quotient rule. So low d high with respect to x is 1 minus low d high minus high d low, which is a 1 over low squared. All right, so we work that out. The x's are going to go away, and I get z minus y over x plus z squared. Let's do the partial now with respect to y. There's only one y. So I'm going to think about it this way. I'm going to write it off to the side to help you guys visualize it. I get x over x plus z plus y over x plus z. So the x part just goes away. That's a 0 because there are no y's. And then the second part, I just get 1 over x plus z. It's like a constant times y, right? Like 3y, if I take the derivative, I get 3. Well, the constant here is just 1 over x plus z times y. It's the same thing as 3y, just a different constant that looks a little janky. All right, let's do with respect to z now. Okay, this one's a little more complicated. We do have to do the product rule, but we only have to pay attention to the z. So low d high, that's 0, minus high d low, all over low squared. We could have probably done this a different way too. I'm just not afraid of the quotient rule. You shouldn't be either. It's really not bad if you actually use it. So there we go. We have fz of that part too. So the gradient of f then, of xy, remember this is our steepest path from a point. This is going to be z minus y. I'm going to get rid of that parentheses because we're going to have some here. Z minus y over x plus z squared I plus 1 over x plus z j, and then plus, and then I'm going to throw minus there and then change the top to x plus y. Notice it would distribute x plus z squared. You don't have to do that. You could have left the negatives and still got the right answer. All right, so we have that, but they didn't want just that. Okay, now notice I actually wrote this wrong. This should be f x, y, z. All right, we have a third component. So they want us to find del f of 1, 2, 3. So we plug everything in. I'm going to help us out with time because I'm making one video for this section. We get 1 over 16i plus 1 over 4j minus 3/16 k. All right, that's it. So that is the vector. If I'm standing on top of this surface, remember we have a 3D surface. I'm standing in the middle of this surface. It's like a hillside or a blanket. A blanket's a weird one to think about, but like a hillside, some kind of landscape, and I'm standing in the middle of it. And if we put some coordinates on there, some axes, I'm standing at 1, 2, 3. X is 1, 2, y is 2, and z is 3. And if I want to know which way is the steepest way up, that vector would tell me which way to go. Okay, so far we've been good. This is just del f. Let's practice some directional derivatives. So they give us this. The first thing that we need to do always, and I'm going to write step 1 after this. Actually, let's wait. Let's do steps. So step 1, forgive me. Step 1 is going to be find. So they want the directional derivative. So find del f at a point. Okay, so del f, I write down the definition, so I start memorizing fxi plus fyj. Remember, it's a vector because it's directions, right? So now I need to plug in that thing with respect to x, all right? So the 1/2 comes down. I get x squared plus y squared plus 1/2 to the negative 1/2 times the chain rule with respect to x. It's going to be 2x I plus, it's going to be the exact same thing, but with y, with the 2 at the end. Okay, we have that. And then we're going to go ahead and find del f of that point, 2, 2. This is going to be the steepest way up. So del f of 2, 2. I just plug 2 into everything. We end up getting 2/3 I plus 2/3 j. This makes sense. It's going to be the same because the only difference was the x and the y. All right, so now that tells me my gradient at that point. So if I'm standing at 2, 2 on this surface, if I walk in that direction, it's the steepest way up. All right, step 2 would be to find u. And I'm going to go ahead and put in capital letters here because this is where all the mistakes come from. Unit vector. Has to be a unit vector. So I'm going to just use the vector that they gave us and create a unit vector out of it. We do that by dividing by its magnitude. All right, so I have the vector 3, 4. All right, hopefully you can see the magnitude. It's 5, 3, 4, 5 triangle. So we get the vector 3/5. I'm switching back to ij and k since the one up there is that way too. 3/5 plus 4/5 j. And then step 3, the reason we found both of those is now we just know that the directional derivative is the dot product of those two. Del f dotted with the unit vector. So I have 2, 3, 2, 3 dotted with 3/5, 4/5. Once we multiply and add all that out, we get 14/5. This is a slope of that surface. It's a tangent line, slope of the tangent line at the point in that surface. This is not the fastest way up. That doesn't make sense to say that's the fastest way up because 14/5 is just a number, it's not a direction. So that is the slope of the tangent line in the direction of u on the surface at 2, 2. All right, let's get some more examples in. Now I have this directional derivative of that function at the point 2, 0 in the direction of the line from P to Q. All right, so same steps. Step 1, find del f. Okay, so I write the definition of del f, x, I, f, y, the partials. Okay, so now I need to find those partials. The partial of that thing, there's only one x, so that's great. That's just negative e to the y. Partial of y, we get negative x e to the negative y. There's just one y, so there's no product rule. Right, so that tells me that del f, go ahead and put xy, I guess, xy equals e to the negative y I minus x e to the negative y j, and we are working for the point 2, 0. So y is 0, okay, I get I, y is 0, x is 2, I get minus 2j. So that is the gradient at that point. Now, this is just a direction, right? This tells me which direction to go if I'm standing at 2, 0 and I want the quickest way up. Step 2 was to find the unit vector. All right, so they gave us a p, 2, 0, and they gave us a q, negative 1, 2. And we're going to find the vector pq, and then we're going to make it a unit vector. All right, so pq is negative 1 minus 2 is negative 3. 2 minus 0 is 2. But I want a unit vector, so this is going to be pq divided by the magnitude of pq. Right, pq is just negative 3, 2. Divided by its magnitude, which is going to be, if you run that, it's the square root of 13. So this is the vector, and I'm going to put it in ij form because the one above is plus 2 square root of 13j. So there is my unit vector. That should have been number 2, not number 1. Number 3, the third step, is to find the directional derivative of f to 0, and that means just take the dot product of the gradient at 2, 0, and I dot it with my unit vector. So we have the vector 1, negative 2, dotted with negative 3 rad 13, 2 rad 13, over. Anyways, okay, and I do all that, I get negative 7 rad 13. Work it out, you double check that. We found the slope. So we have the slope of that tangent line that goes through that point on that surface. I'm going to keep just giving you, I have one more, and then I have an application, and that's it. All right, so here's our last example of just a straight directional derivative. Notice they gave us the 3 components, so this time we're going to have order triple for our gradient, and it's the same like the last problem, except for now we're dealing with x, y, and z, 3 variables. We were in 3 dimensions still, but now we're thinking, if we think about this actually, this graph is one more than the number of variables, so this is a 4D graph. So it's even hard to even understand what we're looking at, but we can still think of this tangent line. Okay, the first thing says find del f. Del f is the partial of x, I, plus the partial of y, j, right? So I need partial of f with respect to x. Okay, this is just, I'm going to rewrite it right here, x, y, z to the 1/2. So 1/2 comes down, I got x, y, z to the negative 1/2 times yz. That's the chain rule, the derivative of the inside with respect to x. Okay, this gets me, okay, it's going to be yz over 2 times the square root of xyz. Okay, you can see the symmetry that's going to happen here, and I'm just going to write them down. We get, for y, we get xz over 2 times the square root of xyz. Sorry for my handwriting, I don't know why it's so squiggly today. I guess it usually is, but so we have f, and then now I can even write down z, because z is going to be symmetric as well. I get xy over 2 times the square root of xyz. If you don't trust yourself with symmetric stuff like that, go ahead and figure out the derivative again. There's nothing that's going to harm you doing that. I'm not going to write all that again. I'm just going to do del f at the point was 4, 2, 2. So I'm going to plug in each component there. Once we do that, we get 1/2 I plus 1j plus 1k. Kind of crazy, it works out that way. So you would just plug 4, 2, 2 in each component and get them there. Right? Step 2 was the unit vector. Right? Unit in capital letters. That's where all my mistakes are for my students, is they don't make it a unit vector. Right? They gave us a p, which was 4, 2, 2. And then they gave us a q, which was 6, negative 2, 6. So the vector we're going to be running along is PQ. That is 6 minus 4, which is 2. Negative 2 minus 2 is negative 4. And then 6 minus 2 is 4. We need a unit vector, though, not PQ. So we are going to take the magnitude of PQ and divide by it to create a unit vector. All right, so the vector itself is 2, negative 4, 4. And we're going to divide by its magnitude. If I put all that in there, I get a 6. All right, so I get 1/3 minus 2/3 positive 2/3. Right? Then 3, we find our directional derivative. Right. When we wrote our gradient up here, we should have put a third component. We did it, but I didn't write it there. Okay, directional derivative is going to be my f, the gradient f, sorry, dotted with the unit vector. So we get 1/2, 1, 1, dotted with 1/3, negative 2/3, 2/3. Once you do that dot product, I'm not going to waste time on the video doing a dot product, we get 1/6. This is the slope, right? The slope of the tangent line in that direction on that surface. All right, let's take find us a word problem here. So a part of a certain hillside can be modeled by that function. So we have, this is a surface, right? This is 2 variables, so this is a 3D graph. So it makes sense that this could be some hillside. You are at a point, 3, 2, or we can think of Z, 2. And at the bottom of the canyon, at the origin or apaca, I put stormtroopers. Could be arbitrary. Anything's chasing you. I put stormtroopers because Star Wars was on when I was writing this. These stormtroopers are about to chase you. Okay, so it says find the direction of the fastest path up the hill. So we'll imagine that you're on some kind of vehicle that going up the hill is not a problem. No hill around you on this planet is going to be an issue. So the best way to get up that hill the fastest is to go up the quickest, the steepest path. Even though we know probably in the real world, the steepest path would maybe not be the best choice if we're trying to get away fast. But it could be. So we are going to try to find the quickest path out. Well, the quickest path out is our gradient. All right, our gradient is the partial of x with I, and then the partial with respect to y, j. So I just need to find each part of this model. All right, that is just 2x plus 3y squared to the 1/2. Okay, the 1/2 comes down. 2x plus 3y squared and then this becomes a negative 1/2, and then the product rule, we get a 2 from the inside. So the 2's cancel, that's nice. We get 1 over the square root, we can go ahead and throw the square root on there, square root of 2x plus 3y squared, right? The 2's canceled. Partial with respect to y, it's not symmetric in this case. The 1/2 comes down, I get 2x plus 3y squared, still that stays, it goes down to a negative 1/2, but now I take the partial with respect to y, so I get the 6y, leaving me with a 3y on top. All right, so this gives me my gradient. I could write this out. All right, this is my I component, that's a 1 on top, plus, and then 3y, or the same thing. The good thing is plugging it in is not going to be too bad here. All right, so now we want the gradient, though at the point that we're at, the point was 3, 2. So we're going to plug in a 3, 2. Okay, what do we get in that bottom there? We get a, plug in 3, we get 6. If I plug in that, I get 12. I get square root of 18. So we're going to get 1 over the square root of 18, I, plus, right, and I plug in a y there, I get 6 over the square root of 18, j. That's a great answer. So this is the quickest way out of that canyon, right, to get past them. We're also, let's go ahead while we're here, and we'll end the video with this, the max rate of change, and we mentioned this in passing, max rate of change, we mentioned this in passing at the very beginning of the video. The max rate of change is just the magnitude of del F at that point. So we end up getting, if I run the magnitude of that, we get 70, square root of 74 over 6. So that is from the point 3 to the slope that is the steepest. That slope is root 74 over 6 in the direction of del F. This is pretty great stuff. Where I see this, one of my best friends is a storm chaser for one of the stations in Tulsa, the top storm chaser for Channel 2, if you're in this area. I chase with him sometimes, and what that means is I go sit in the car for hours, and then we see a little bit of action. But when I'm with him, he's looking at radars and everything, and we actually see a bunch of vectors pointing in different directions. We get what is called a vector field. And in this vector field, and we'll talk about this later this semester, this is the way that our wind is pushing, and the gradient would be very interesting to us because it would be, if we're looking at how wind is moving, right, and we're considering that as a surface in some way, we can find the quickest rate of change using the gradient. My storm chaser friend knew what the gradient was. Does he know about the the math side of it and understood this vector stuff? No. He just knew, looking at a picture that shows change, he can find the gradient by finding the fastest change. What they have is they have like almost a contour level, contour map of velocities. So you can see when velocities are changing the fastest. So that's my real life application. He actually uses that to help him chase out in the real world. He's looking for the gradient half the time when he is chasing. So like I said, the gradient is super, super important. We're going to keep using it. It's going to keep resurfacing because we're going to do some crazy stuff in 3 dimensions towards the end of this course.